So yeah, my name's Paul Gross. I'm a developer at Braintree. I've been at Braintree about 3 years or so I know a lot of stuff. So if you have questions that I don't cover about Braintree or some of our technology stuff, feel free to ask me afterwards. Okay, so Braintree is a payment gateway. And what that means is it's basically software to allow you to process payments online. We typically do credit cards. So these are some of our merchants. Hopefully you recognize some of the names. We're pretty proud of our merchant list. But basically the way it works is if you go to GitHub and you want to pay for the service and you go to their form and you type in your credit card information, you hit submit, basically it comes to us. We handle the credit card, we do all the payments related stuff. We charge the cards, we deposit funds, we do things like vaulting, so we store cards. So that's kind of, basically what we do. Think of us as like the payments related stuff for these companies. So for us, the question is, why is uptime so important? For many businesses, it's not. Obviously Twitter, uptime not that important. But we care pretty deeply about uptime. Last I checked, we do roughly $5 billion in annual processing. So that comes out to be about $9,500 a minute. So for us, $900 a minute is a lot of money for our merchants. So when we're down, not only do we lose money, obviously, because we take fees on the credit card charges, but our merchants are losing money very, very quickly. Furthermore, since we're kind of behind the scenes, like I'm sure many of you went to some of those merchants and didn't know that your payments were coming through us. When we're down, it's possible that those sites also look down. You can't sign up, you can't pay, and so it basically makes them look bad, even though it's really our problem. And so we hate that. So for us, because it's expensive, we don't want our merchants to look bad. We care very deeply about uptime. So people kind of talk about nines, how many nines of uptime you have. Not everyone really knows what these mean. So I pulled up this chart from Wikipedia. It's trimmed down a little bit. 5 nines is kind of the one people always talk about striving for. 5 nines is extremely difficult. It's about 5.5 minutes of downtime a year, which is about 26 seconds a month. So that means that, if let's say your primary database crashes and it takes you 10 or 15 minutes to get that back up manually, like you've blown 5 nines for that year, and the most you're going to do is 4. So, these numbers are extremely hard to get to. Even 4 nines is 4 minutes a month. So that's not a whole lot of downtime that you give yourself, wiggle room there. So at Braintree, for various reasons, and I'll kind of get into later, uptime is very hard to measure for us. But we strive for 5 nines. I would say, we don't always make it, but that's kind of what we shoot for. Okay, so I'm going to cover 2 kinds of downtime in this talk, planned and unplanned, and the kind of the strategies and the techniques and the software we built to kind of handle both of these. So first, planned downtime for us is, reducing maintenance windows. There are times when we obviously need to take a maintenance window, and how we can get that smaller. So I'll just give you a little bit of background. Braintree, the main gateway code base, is about 4 years old, and it started at the time as a pretty typical Rails app. It ran on MySQL. It used Apache and Passenger, kind of standard stuff at the time. So at the time, maintenance for us, the biggest one was rolling out new software. So our typical pattern was to push out new code to servers. Then we would throw up a maintenance page. We would run database migrations, and get the new schema out to the state we wanted it to be in. And then we would restart Passenger, and then we would take down the maintenance page. So for us, the biggest source of our planned downtime was basically how long the database migrations took to run. So early on, we actually switched from MySQL to Postgres. A lot of other people here have been talking about Postgres. We also think it's an awesome database. We run a ton of stuff on it. But the main reason that we switched was the migrations are extremely fast in Postgres. So in MySQL, if you add a column, remove a column, rename a column, it basically copies the entire table again. And as your data gets bigger and bigger, and we store a ton of data related to every transaction that we do, it gets slower and slower to the point where you're talking minutes. I've been on projects where I've seen they have migrations that take hours to run. And for us, we're down for that entire window. That's just unacceptable. So Postgres, no matter how big the table is, adding a column, removing a column, renaming a column is just milliseconds. It's extremely fast. Postgres also gives you the ability to add indexes without locking tables. So again, in MySQL, if you want to add an index, the site's going along, we find a new way people are querying stuff, we're missing some indexes. If you want to add that index, it actually locks the table. Some of this may not be true with modern MySQL, but this is the way it was, years ago when we were doing this stuff. It would lock the entire table and the site would basically become unusable for some amount of time. Postgres has this keyword concurrently on the create index, and it lets you do it while the site is up under no impact. Obviously, your database might run a little bit slower for that period of time, but for us, it's generally unnoticeable, and it means the site can stay up. And then the other big one was transactional DDL. So we use Rails migrations. A given migration may have multiple statements in it. With Postgres, they all can run inside of a transaction. So that means we're rolling out a new version of the software. The first three the first three things work. The fourth one, let's say, fails. With MySQL, your database is now in a hosed state. You have to basically manually either finish the migration or roll the whole thing back. With Postgres, the whole thing rolls back at once, and we can just put the old code back. So even under cases where a deploy didn't go so well, we could easily roll back to the old code, roll back to the old schema, and get the site back up quickly, without too much downtime. So actually, I'm not going to go into too much more detail on this. I did a talk on this whole topic, and you can find my slides online. I'm going to post the slides for this talk afterwards, so you don't feel the need to run and kind of write down this URL. But I did a whole talk on just kind of all the stuff around migrating. It wasn't super easy, but it's very doable. So given this now, our deploy process today, a little bit different than what I described before. We basically, while the site is still up, we add new tables and columns. So we do as much as we can, before we're going to take our downtime. And then currently, the way we do most of our things is we actually roll out the code server by server. So on every app server, we push out the new code, we restart the app, and then we go to the next one. And so there's actually no downtime. We're kind of going piece by piece rather than taking the whole thing down. And then once the new code is fully rolled out, we go through and do things like adding indexes and other, sometimes you need to populate tables and other things like that. And we do that, like I said, at the end when the site's back up. So this approach has no downtime. So this is basically the code we wrote to do this. Similar to DB migrate, we just added two new folders, migrate pre and migrate post. We just basically looked at how DB migrate works, and you copy the 2 lines of code. And we use Capistrano to do deploys, and we basically run migrate pre, do the normal Capistrano deploy stuff, and then we run migrate post, and it's very straightforward. Okay, so the downside, or one problem with this approach, is that Rails caches columns. So we can add new columns in a pre-migration, but once the new code is out, we actually can't drop columns. As soon as you drop a column, even if none of the code is using it, Rails has cached it, and you start getting errors trying to insert into a column that no longer exists. So what we needed was a way to tell Rails to forget the column so that we can then clean up old columns that we're no longer using. So this is kind of the code we wrote. Again, this is heavily simplified for slides, but now we have a way in our active record models to say deleted columns, and that code looks like this. So that method is defined in active record base. It basically just stores the list of columns that have been deleted into an instance variable. And then we used alias method chain. This is Rails 2.3. That's what our primary gateway stuff is on. We used alias method chain to basically intercept columns and then remove all the ones that we've tagged, essentially. So now, whether it's us or Rails calling columns, it returns without any of the ones we tagged. And now, when this code has been fully rolled out, we can drop columns on the fly. Like I said, they only take a couple milliseconds in Postgres. It's not a problem. Postgres does require a lock, but it's super fast at getting it, super fast at dropping the column. The site has absolutely no impact. So this is basically the way we do our deploys. The thing I kind of glossed over there is we actually run multiple versions of the code at once. So because we roll code out server by server for a given period of time, usually maybe a couple minutes, we have both the old version of software and the new version running at once. It turns out this is actually fine for most things. We do, I would say, like 95% of our deploys this way, 95% of our code releases. It's usually not a problem. For example, you're adding some new logging, or let's say we're passing a new field downstream to processing networks. For some period of time, some code will get it, some new logs will appear, some won't. Eventually, they'll all be there, and it's not really a big deal. There are obviously cases where we can't roll out features this way, and so for those, we use feature switches pretty heavily. So we'll roll out features dark, and then once the new code is fully rolled out, we'll turn it on, and we have the ability to turn it on for a given merchant. So let's say we want to turn it on for a beta merchant and kind of watch the feature, make sure it's good. We can do that. We can turn things on globally as well. So we can just turn it on for all of our merchants all at once. And so that's just kind of like the way we still do server by server deploys with multiple versions running, but actually control features turning on or off kind of atomically. So, like I said, there are limitations. That's the way we do probably 95% of our deploys, but there are obviously some things that don't work with this approach. The big one is column renames. So column adds and column deletes are very easy. Column renames are near impossible. There's really not a good way to run multiple versions of the code and also do a column rename in there. So you just can't do it, essentially. Things like database failover. So let's say we know we need to take a maintenance window because our primary database needs like a security update or something like that. Nothing I've really described so far would handle any of that. And then just larger infrastructure changes as well. If we need to change out some of our infrastructure, we need to do some big upgrades, things like that. Nothing I've really talked about handles that. So what we really want is a way to pause traffic. So this is kind of the thing we're missing here, is that the server by server works really well, but what we really want to handle all the cases where that doesn't work is a way to pause traffic and not lose traffic, not put up a maintenance page and say that we're down, but just pause it for some amount of time so that we can do what we need to do and then resume traffic. So this is our simplified architecture today, and I'll go into it in pretty good detail, but the important thing to note is that we have a load balancer or a load balancing layer going to multiple Apaches. I've drawn 2 here, but we have N. And then we have a couple components that you probably don't recognize. One is the proxy, and then one are dispatchers. I'm going to go into detail on those in a moment. But basically, traffic flows in through Apache. Apache serves all the static stuff. Anything that's dynamic goes to the proxy. The proxy puts it into a Redis queue. Dispatchers read off the Redis queue, and then they do all their work. So the proxy stands for Braintree proxy. It's not very clever, unfortunately. They say that one of the hardest things is naming things. Obviously, we failed here. Okay, so again, forgive me. It's not Ruby. I'm going to speak on a little bit of Python at a Ruby conference. It's probably horrible, but it's a Python tornado app, and it's evented. The big thing here that we wanted was evented. So this, from that diagram, all of our traffic is flowing through this thing. It's going to be holding tons of open connections. Some of them, longer lived. So we wanted something very efficient that can hold lots of open connections and do lots of good network traffic. And so we wanted an evented component, essentially. At the time, we looked around, and we really liked Tornado for a variety of reasons. You can talk about it with me later. You can yell at me later if you like as well. So like I said, it basically accepts web requests from Apache. It feeds those requests into Redis as a queue. And then it reads responses from Redis coming back up the stack and responds back out to the proxy. Back out to Apache. So that's like the top half of it. The bottom half is the dispatchers. These are lightweight rack adapters. This is Ruby. These things take requests from the Redis queue, and they process it through Rails. So we still use Rails with this architecture. It's a little funky, but the dispatcher is the glue between kind of our interesting infrastructure and actually Rails code. And then once it processes through Rails, it gets the response that would normally be served back out. Instead of serving it kind of the way Rails typically serves a response, we put it back into Redis. Yeah.
So these dispatchers, they're processing pipes and total messages.
Yep. Yep, and I'll kind of illustrate some of that out as we go. So here's what the code looks like for the dispatcher. This has been shortened to fit on slides again. Basically, it's a Ruby file. It requires environment. So basically, at this point, it's got all of Rails loaded. It then creates a rack app out of the action controller dispatchers. So it's using the Rails code to basically create a rack app. And then in a big loop, all we do is pull data off of Redis, and we build rack requests. So a rack request is just a big hash. I've only shown 2 of the arguments here, but in reality, it's like a 10-argument hash. And we build that hash out of the things that we get from Redis, from the proxy. And then the last line you can see here is we basically do app.call. So we basically process through rack, through all the Rails middlewares, all the normal Rails code that you would normally use. We process through all of that, and we get back the rack response. Then we turn that back into a string body, and then we push that back into Redis. So here we push back the status, 200, 500, 303 kind of thing, and the body, and a few other things that I've taken out for brevity. But this is pretty simple. The dispatcher is, like I said, literally just glue between Redis and Rails, and that's all we really use it for. So here's the diagram again. Yeah.
Does Apache keep connection throughout this whole time?
Yep. So Apache's keeping the connection, and the proxy's keeping the connection open. We use Apache just as a proxy. So it's doing like mod proxy through the proxy. So now when we want to pause traffic, all we have to do is stop these dispatchers. So they stop, the whole top of the stack keeps working, requests keep coming in, and they're just waiting for responses. They keep flowing into Redis. The Redis queues get bigger, obviously. But at this point, nothing is using the bottom half. So the database is unaccessed. Nothing's using our search services. We can basically do any kind of maintenance we want. We can do database failover. We use this for actually switching between data centers at one point. We can do, quick upgrades, things like that. Anything, basically anything we can fit in about 20 to 30 seconds. And then when we're done, we start the dispatchers. They flush through the queue very quickly, and everything starts working again. So with this approach, we'll have a few long running requests. Generally, like I said, we try to keep it around 20 to 30 seconds. But that's better than giving an error or timing out. So you may, every once in a while, when you go to check out, you may see a couple long requests, but it will go through, and that's the big thing. It's no downtime. Yeah.
If a client starts connecting and sends a request and then cuts it off for some reason, does the request get removed from Redis?
Both the Apache and the Proxy have things in there, but basically it doesn't make it down into Redis until the request is until we've gotten the full request.
Yeah, so let's say the full request comes in and then...
Oh, then the browser stops? No, so we don't have anything that actually removes it from Redis right now. So that request will generally still process. Actually, the Proxy, I think, does some stuff around that, but it's not perfect. Generally, we're not a site serving a lot of, we're not like a Twitter or Tumblr. People generally process payments through us. So we don't have a lot of people kind of leaving. Generally, when someone processes a payment, they want it to finish. Most people connecting to us are merchants through our API. So we don't, again, we do have a control panel, people look at it, but that's a small fraction of our traffic compared to actual payments coming through. So we haven't really noticed it being a problem because, like I said, most of our requests are important. Okay, so just to kind of summarize what I've talked about so far, we do as much as we can while the site's still up. So we use pre and post migrations for that. We do rolling deploys so that we can, roll out code server by server. This also helps us reduce risk. Let's say we roll it out to one app server. All of a sudden we start seeing errors. We can stop rolling it out. We can stop the dispatchers on that server, figure out what happened before we take it out to all of our servers. And then we use Postgres largely because it's super fast at doing schema migrations and, being a quick moving gateway, we do lots of code deploys. We do lots of schema changes. We're constantly rolling out new features. And then for everything that doesn't fit into this model, we use the Proxy to pause traffic. And we use this one less often, but because it is a little bit riskier, we're obviously pausing traffic, but it works out really well to pretty much do anything that we can't fit into a normal server by server deploy. Okay, so that's kind of the planned failures section. I'm going to talk about unplanned failures now. As we all know, servers will fail, networks go down. The unexpected will happen no matter how much we plan. Things that we don't expect will happen in our data centers and in the world at large. And basically, we do our best to be resilient. And I'll go through a lot of the strategies that we do here. So start with server failure. So the way people could typically handle server failure is load balancing. We're no different in this regard. The thing we are different about is that we build our own load balancers. So in general at Braintree, we like to control every component of our system and really understand it and be able to tweak it, again, for availability and things like security. So what we don't really like are black box load balancing appliances. I know they work really well for a lot of people. A lot of people also love to complain about them. So what we like is, kind of custom built systems that we understand truly. So our load balancers, we run LVS or IPVS. This is the Linux Virtual Server project or IP Virtual Server. They're basically Linux boxes with kernel level routing. So what IPVS does is it lets you, so traffic flows into a load balancer, let's say, and then through various IPVS kernel level rules, it will get routed to multiple backends. And I'll go into some detail on that in a moment. We use pacemaker to manage the cluster. So if load balancers die, pacemaker does failover. And then we have two components that we wrote, Big Brother and Litmus Paper, and I'll talk about how these work in a moment. So this is kind of this is the simplified diagram of our load balancing. So traffic comes in either through the internet or through internal services. We load balance our internal services as well. It comes to a pool of load balancers. Here I've drawn 3 that are run by pacemaker. So the virtual IP lives on one of the servers. So when you go to www.braintreegateway.com, that maps to an IP address living on one of our load balancers. That load balancer bounces over multiple backends. Here I've shown 3 Apaches. And then I'll explain Big Brother and Litmus Paper, but the important thing to note is that Big Brother runs on the load balancer, Litmus Paper runs on the backends. And this is our stack. So Big Brother, it's a Ruby app that we wrote. Like I said, it runs on the load balancers. Its job is to check the status of backend servers. So every second or so, it's checking all of the Apaches to make sure that they're all up and good. And then its job is to update IPVS rules. So if it queries one of the backends, it discovers that Apache's down, let's say, it will change the kernel level routing to take it out of the load balancing pool. When it comes back up, it will change the routing again to put it back in the pool. It's open source. You can check out the source of Big Brother on our GitHub Braintree account. So the other side of the piece is litmus paper. This is another Ruby app that we wrote. This one runs on the backend servers, and it's queried by Big Brother via HTTP. So every second when Big Brother is polling, it's actually polling litmus paper. And the whole job of litmus paper is to return a health. So litmus paper is a standard interface for Big Brother, and then it does whatever it needs to do to figure out the health of that box. So for something like Apache, it may just turn around and curl another URL. For other types of backend services, it may do something more complicated. But its job is to say, I'm up and I'm great, health 100. I'm up, but I'm running a little slow right now, health of 50, and Big Brother will adjust the rules such that it takes less traffic now. Or I'm down, health 0, and Big Brother will remove it from the pool. And litmus paper is also open source. You can check it out. So here's the diagram again, just to kind of show you how it all works. So, this I've shown here one virtual IP, but in reality, all of our load balancers have multiple IPs. Some of them external, some of them internal. We balance over tons of back-end stuff. We balance over almost everything we have, and it works well. So that works really well for stateless services specifically. So something like Apache, where traffic can code to any Apache, it doesn't really matter, But there's also stateful services. So for example, our load balancers are stateful. The virtual IP, as I said, lives on one load balancer, and only that one load balancer should take that traffic. Postgres is stateful. We can't send our database traffic to all of our databases because some are primary and some are standbys, and you don't want to send writes to a standby server. And so we have this idea of some of our servers are special. They need traffic, but there are other ones waiting to pick up the traffic if they crash. And so for these we use pacemaker. I already kind of went into the load balancer pacemaker, but similar thing. If a load balancer crashes, pacemaker will take it out of the cluster and move all of the IPs to another server. If Postgres crashes, like our master crashes, pacemaker will promote a standby and then it'll move the IP to the new standby. So the app, so externally and uses the same IP. The app all use one IP, and the idea is no matter what kind of failure happens here, the IP will move. So the app, we don't need to change anything in the app when our database crashes. We don't need to change anything when our load balancer crashes. It all kind of heals. So that's server failure. Now I'm going to talk about network failure. So there are a couple fun sites I'm going to show you. This one's outages.org. It maps ISP outages across, I believe, the world. This is a map of the US. This is a 6-month period, and you can see there are 32 outages on the East Coast. You can pretty much see where a lot of the major data centers are by where these circles are. But you can see that, outages are not uncommon. This is a fair number of outages of ISPs. Another fun one is Internet Pulse. We use this one a lot. This one actually shows you the breakdown of ISP to ISP connections and the problems that are there. So if you look at the top, there's a red box between Savvis and AT&T. So that means, let's say, Savvis is one of our ISPs that we use. If you're on AT&T, you might have trouble connecting to us. At the bottom, you can see Verizon's having trouble connecting to both CenturyLink and Cogent. So these, if you go to these pages today, it's likely you'll see yellow and red boxes. There always seem to be some problems. The internet as a whole is very resilient, but individual links do go down a lot. So it's definitely something that we do have to handle. So I just think these are fun. So I'm going to talk about, I'm going to break networking into two pieces. So the first is inbound. So this is, you go to GitHub, you enter your credit card, you hit submit. GitHub's got to connect to us. So this is traffic coming inbound to us from merchants trying to do things. So here we use BGP to basically route traffic through multiple data centers and multiple ISPs. So BGP is the Border Gateway Protocol. It's basically the protocol of the internet. It's how traffic is routed on the internet. So if you want to connect to a certain IP address, you use DNS to go from a name to an IP address. Now you have an IP address, you want to actually send packets there. BGP kind of controls the routing from where you are to where you want to go. And there's usually multiple routes to a location, and BGP kind of picks generally the shortest path. So, our routers in our data centers participate in BGP. So we broadcast routes, like I said, in multiple data centers, multiple ISPs. So there's multiple ways to kind of get to us. So back to the internet pulse, like if one route is down, those routes will unbalance, and people will still be able to connect to us through a different BGP route. So this is, it's not something I would say most Rails shops deal with, but it's very handy for kind of working around issues. And then we use things like Pingdom, which is a monitoring service. We have our own kind of globally distributed servers running on various ISPs, and we basically just use that to test it. So BGP is great. It's not instantaneous. When ISPs go down, it usually takes a few minutes to unbalance. And we've seen cases where partial ISP outages actually won't unbalance very well. And so we'll use Pingdom, we'll use our own servers, and we'll manually yank BGP routes. So if we notice like one of our ISPs is having trouble, but the routes are still there, we can manually yank those routes if we have to, and force traffic to come in through another path. So it's kind of one of the hammers that we have to deal with here. Okay, so that's kind of traffic coming to us. There's a whole other set of traffic that we deal with, which is outbound. We are not the end goal for most API requests. We need to connect to the processing networks to actually charge the cards. There's a lot of processing networks depending on what country you're in, where your merchant account lives, sometimes what card type you have. Like we have multiple networks that we need to connect to. I already showed you the graphs of ISP outages. ISP outages are often partial as well. It's pretty rare for ISPs to totally crash. There was a big one in Chicago not too long ago where I think they were doing some construction and they just like dug right through a line and took down an entire major Chicago ISP. But generally they're partial. Some router will fail in some ISP and some connections will fail. So, I talked about the hammer of like totally yanking BGP routes for one ISP. In general, that's actually not good enough because there are partial outages, we need to be able to connect to each processing network on each ISP. And sometimes we can connect to some on one and some on another, and we don't actually have the whole set on either one. So we can't just yank an ISP, we need to be more specific. So what we wanted was basically a way to route such that we could, for a given endpoint that we are connecting to, choose the best ISP. And so what we built there, we call them processor proxies. So like I said, instead of connecting directly, we connect through these proxies. We run a proxy per endpoint and ISP, and then we load balance over them. So we have a pool of these things. If an endpoint goes down for a given ISP, that piece of it will unbalance, and we can route around it. And so that's kind of the way we handle outbound connections for ISP failures. So that looks like this. So the software we use for that is Mallory. I have a diagram in a moment. So again, it's Python Tornado. For a lot of the same reasons as the proxy, we wanted something evented. It's basically just a network proxy, so it's doing tons of open connections. It doesn't really do much except for shuttle traffic back and forth. It proxies these requests. It does SSL verification. So this is like the big thing about why we wrote Mallory instead of using something off the shelf. A lot of our endpoints use SSL. And one of the benefits of SSL is encryption, but a bigger benefit is actually verification. So when we connect out, we want to know not only that the traffic's encrypted, but we're connecting to who we say we are. We're not getting a man-in-the-middle attack where someone's reading all of the credit card data that we're passing up. And actually, a lot of the proxies out there don't do SSL verification. That's a big reason why we wrote our own. And the other fun thing about Mallory is it acts like litmus paper. So similar to how litmus paper ran on the back ends and returned to health, Mallory returns the same contract. So not only does it proxy, but as Big Brother queries it, if proxying is not working so well, when Big Brother queries it, it can actually say, oh, health 0, and actually pull it out. So it's both doing the proxying and keeping track of how well it's going so that it can return a health back up to Big Brother. So Mallory is also open source. You can check it out on our Braintree page. So this is the diagram of how it all works. So the dispatcher is the Rails app, as I've talked about. We need to make a call out to a processing network to, let's say, charge a card or verify a card. So the top is processor 1, the bottom is processor 2. Let's say in this case we're going to make a call to processor 1. So we make a call to an internal IP, which is a load balance service. It bounces over 2 Mallories, each pinned up to one ISP. And most of the time, both Mallories get traffic, usually pretty evenly. But then let's say ISP 1 is a partial outage. We can no longer connect to the processor 1 on ISP 1. The top Mallory will unbalance. All traffic will route through the bottom Mallory. If ISP 1 has a total outage, all of the Mallories will unbalance for that one. We don't have to do anything special there. But in general, when we look at the Mallory logs, we see like some unbalancing, some rebalancing, but we don't often see total outages. They're usually partial and they're usually short. So, for like a minute or so, we'll have trouble connecting to one endpoint at one ISP, and then it'll kind of resolve itself as either BGP kind of fixes itself, or maybe the ISP, rebooted a router or something, and now it's back. You never really know kind of what goes on downstream. So this is the way we handle that. So, when we have connection failures, like I said, we want to basically let things heal. So with Mallory, we let it unbalance. When our database fails, pacemaker will do kind of the failure for us. So basically, our main goal here is we let the system heal itself, and then we retry. So, if we get a connection error connected to a processor, in the app, in the dispatcher, we'll usually just try again. So, and by the time we try again, it's possible the offending ISP will have unbalanced, and it will work this time. With the database, if our database were to crash, we would obviously lose kind of in-flight transactions. There's not really much we can do about that. Sorry, 1 second. But before we pick up another request from Redis, we actually, do heartbeats of our systems. So if the database were to crash, before we would pick up a new request, we would wait for the database to fail over, come back up, and then we start processing again. Yep.
Do you ever have instances where you send a request to a processor and the connection goes up before you get a response? So you're not running something with the processors.
It does happen. That case is generally less common than we can't actually make a connection to the processor. I'll talk about that. I'm getting a little short on time. I can address that in the question section. So along the lines of kind of what I talked about, it's a little orthogonal, but basically our practice is to automate everything at Braintree. The big one is it reduces human errors. So I've talked about, like if we need to manually pull out BGP routes, sometimes we see ISP outages and, maybe they're partial, but they're not even enough for Mallory to really unbalance itself, and we want to manually unbalance. We have, one command automation for almost everything we do, mainly because we don't want to cause more problems than we solve. You constantly read articles online about someone accidentally ran a command in production that they weren't supposed to, and caused an outage that they didn't mean to. And so, we feel by automating things, we reduce the human factor. And in fact, a lot of our more devastating tasks will actually prompt like, hey, this is production, not a testing environment. Are you really sure you meant to run this here? And you have to say, yes, I really did mean to run this crazy thing in production. Automation also gives us confidence that things work. We're a fast-moving company. Things change. Maybe the way you unbalanced the service yesterday is not the way you unbalance it today. But if you rely on automation, you know that if someone changes the way something works, they'll also change the tasks that are automated. And so we know that these tasks always work, essentially. And we use them in every environment, testing and production. It speeds things up. So, I've talked about our dispatcher pauses. We only have, let's say 20 seconds to do all kinds of work. When we were doing our data center failover, we basically had 20 seconds to do a bunch of work that we had to do. When we do manual database failure, again, there's like a bunch of things we need to do. So by automating, we just speed it up, and we're more likely to get it in that short window. Most of the time when we pause dispatchers, it's only for a few seconds. And in general, it's just less fiddling around in production. The less we can be in production, the less chance that we'll cause some kind of outage that we didn't mean to. So we try to automate everything so we don't have to get our hands dirty in production as much. And we use Capistrano for this. It's probably no surprise. We have tons of Capistrano files. We automate lots and lots of stuff. So just to summarize, we use load balancing for server failure and network failure in some cases. We have redundancy across ISPs, both inbound and outbound. In general, our practice is we let the system heal, and we build things so the system can heal, and then we retry, and then we automate everything. So, questions. So I can quickly address, how much time do I have left? 5? Okay. So we do run into cases where, we've made a call to a processor and we don't actually know the outcome. Generally, we can reconcile those later. We also, I don't think it's common in Australia, but we do support something called auth and capture, which means that when you run a credit card transaction, you don't collect the funds at once. You do an authorization, and then in order to actually get your funds, you do a separate capture. And the nice thing about that is if the authorization times out, you don't know what state it's in, you can do another one. And the worst that will happen is funds will kind of hold on a credit card, but they won't actually charge. And so a lot of our merchants do that just to kind of work around these problems. Yeah.
Question on Postgres failover. If you're master-getting these guys, I'm assuming you have some replicas that are committed from one another to a master. How do you deal with the other replicas when you're doing this?
Yeah, so we do synchronous replication in Postgres, and so if our master dies, a synchronous slave will promote, and since the IP will move, all of the other database servers are following that IP, and since it's synchronous, they're at the same state, and so the new ones will be able to just follow, and then we manually will rebuild the old master once we figure out why it crashed, and then we'll add that to the pool.
So the other replicas are asynchronous.
Yeah, we have one synchronous and then multiple asynchronous ones. Yep. Yep.
How do you cope with data loss between Redis and your dispatchers? Say dispatcher picks up a job and then the dispatcher fails and crashes out, or the server crashes or something, it's holding onto a job and it's no longer execute. How do you cope with that?
So the proxy has a few jobs. One thing is, it enqueues into Redis, but then it also sets its own timer. And so if it doesn't get a response in, I believe it's 50 or 53 seconds, it basically responds up with a timeout. So, yeah.
First, I've got to say I'm blown away, totally impressed by what you guys are doing.
Thanks.
Second question is, you talked a lot about Python and Tornado. I was wondering, what was the motivation for going for Tornado versus something like Twisted, or even better with Event Machine and Ruby? You've got a lot of Ruby stuff.
So the question is why Python Tornado? Basically, at the time, we kind of looked around. We knew we wanted something evented, like I said, to kind of hold lots of connections. We looked around and we looked at what was out there and what was being used in production and what seemed to be very stable. And Tornado having like the friend feed and the Facebook kind of stuff behind it, we knew it was running high volume sites in production and doing very well. Event Machine we'd played with, this is a while ago obviously, and although it seemed to work well, we didn't really know of anyone running it in production under kind of high load at the time. We spiked out Node, we spiked out Clojure, Tornado, and Event Machine, and just of all those, we like Tornado. Tornado also has some really nice stuff for testing asynchronous stuff. So Tornado has facilities for spinning up servers, running requests that are, evented async requests, and then shutting it all down. So we really liked the development style as well. In the back?
Is the architecture Proxy just
So it does give us other benefits. It also does rate limiting. So, today, I guess without it, one merchant could basically flood us, let's say, or a malicious person, let's say they create an account and they just flood us with requests. So one of the things that Proxy does is it keeps track of, all of the open requests and and the Proxy has some knowledge of how many dispatchers we have. And so as we get close to capacity, it will actually start holding requests back for merchants that are flooding us. So we won't let any one merchant kind of flood our system. So it also does that kind of stuff. Yeah.
Are you concerned at all about, with Proxies, since Redis is an in-memory database, are you concerned about receiving a very large post body, reading that into memory, and then putting that into memory on Redis again?
Because everything is so transient, it's not really a problem for us. The longest a request will take is a minute. So we only really keep a minute's worth of traffic in memory. And we have our own data sets, we have our own hardware. All of our hardware has, we're not kind of constrained by the AWS memory limits, so we have lots of memory in all of our servers. So it's not usually a problem. I mean, there are cases, we have run into cases where huge post bodies will come in and Python Tornado will be a little weird about it. Sometimes it'll slow down. But modern versions of Tornado are really good at handling even large post bodies. Yeah.
So let's say a dispatcher of 500 is whatever, right? Does another dispatcher pick up the same request and retries?
No. So we basically just do one try. So if we get a 500, we have tons of monitoring and alerting stuff that I didn't talk about. So we get a 500, someone gets paged. It doesn't, at that point it's not really good to pick it up again because it's probably just going to 500 again. So we basically let it 500, we get the page, we look into it, we usually alert the merchant, or we fix it, very quickly and figure out what happened. So, yeah.
Yeah, I was going to ask about, do you use sort of multiple views of the Redis thing Proxy stuff in the front to roll out new code to some people or something like that?
Not really. I mean, we use feature switches to roll out code to some people. So we do kind of handle it at the dispatcher layer. We don't really do anything with the proxy to kind of roll out new code. I mean, the proxy, like that stack I showed you, is most of that runs on one server. So if we need to roll out like new proxy features, we'll basically roll out an entire new stack, a new Apache, Proxy, Redis, its own dispatcher pool potentially, and then we can at the load balancer send some traffic to it, and then kind of swap it that way.
So this thing as you roll dispatchers, roll the servers.
Yeah, no, we don't do anything there. Yeah.
Are you using a gem for the merchant-specific feature tooling?
In the proxy or?
The merchant-specific feature toggling in.
Oh, the feature. Oh, okay. Sorry. Yeah. No, we don't do anything special there. We basically, we have database tables, and one of our tables is merchants, and we have flags on there essentially for different features that are turned on or off. So for us, we want to turn a feature on, we just turn it on at the database level. For features that are on for everyone and have been on for everyone for a while, then we'll just go back and remove the column.
So there's no gem.
No, there are lots of gems for doing kind of feature toggling. We don't use any of them. I mean, I think most of them are written like after some of the stuff that we were doing. But there's some out there, I can't remember the names of them offhand, but there's some that look very cool that use Redis and stuff for global state, and pretty nice. Yeah. Yeah, we use blocking. So Redis has the idea of a blocking pop. So basically, we use that on both the dispatcher and the proxy. So we don't have to pull. We basically do a blocking pop with like a 3-second timeout. And then once, if after 3 seconds, we just try again. And the only reason we do like a 3-second is so when we tell the dispatchers to stop, if they're in a blocking pop, they don't necessarily get the message. So at most, they'll take 3 seconds to shut down, essentially. Yeah.
With pre-migrations, you have your database. You'll have old code looking at your database setup. How do you test that?
So that's a good question. So we don't have a great way to test that like in development. We have QA environments and stuff, and we will generally do our deploys there first. So in QA, we'll deploy the old version, the one's in production, and then we'll do a very similar kind of server-by-server deploy while we generally look at the site and do stuff. It's generally manual, and we kind of just do it in our testing environments, essentially. Yeah, I don't have a great answer for that one. That's a tough problem. Yeah, in the back?
So you've answered why you make the choices in for your event apps. But I was wondering if you had made the same choice now, obviously things like the event machine and stuff like that are a lot more mature these days. You just make the same choice.
I don't know. I can't really speak to that one. I mean, I'd probably do another set of analyses. I mean, like Node has come a long way, Event Machine's come a long way, even Clojure. So we would probably, myself included, just go through all of them again. I haven't really used Event Machine that much because we do most of our stuff with Python Tornado. I also haven't used Node that much recently, so I couldn't speak to that. Any other questions? Yeah.
So with disruptive migrations like renamming columns and changing type, is that just considered downtime?
Yeah, that's when we use the proxy. We'll pause traffic. We'll do that kind of stuff. I mean, it's pretty. We don't do that stuff very often. Even with the fact of dropping columns, like I said, we drop feature switches after we're no longer needed. Generally, features are additive. We generally write new things. We don't often really feel the need to rename columns. It happens every once in a while, but it's not actually that frequent. Yeah.
So a huge part of Uptime is bad code getting through production as well. Causing a downtime for some plans or how do you manage that? Apart from like tests, do you have a rollback switch?
So one of the big advantages that we have is we have a sandbox environment. So if you want to, and I should mention that we support merchants in Australia. You can go to our website, sign up today. We'll get you a merchant account and everything, and it's one sign up form. But basically, one of the advantages, like I said, we have a sandbox account. So if you want to test your integration with us, you would use the sandbox environment before you go to production. So we roll code out to sandbox, usually days before we roll to production. So, I mean, we have run into issues where we cause outages in sandbox, unfortunately, but that's not really handling real payments. And so we can look at that, fix the issues before we go to production. So it's a huge advantage that we have. Other questions? Yeah.
I was curious, obviously you've got lots of tests covering the system. I'm wondering if and how you do automated end-to-end tests, or do you do it all QA?
No, we do all automated stuff. So we use, like, even for local development, we use Foreman. And we run, like when we hit localhost 3000, it's actually hitting a proxy and we're using local Redis and a dispatcher. So even when we're like writing code locally, we use the whole stack. And then we use, in our CI environment, we release client libraries in a bunch of languages, Ruby, PHP, Python, .NET, whatever, all of them. And we have, our CI has tests for each of those libraries, and those use the full stack as well. So all the tests for like the Java client library, go through Apache, the proxy, Redis, dispatcher, everything. So all of our CI is the whole stack.
How long does tests take to run?
They do take a while. We also, it's even worse because we believe in not breaking backwards compatibility, we actually have tests that test every version of every released client library. So like if you're on our client library from a year ago, like that still works today, and we have CI to prove it. So those builds take hours. There's nothing really around it, unfortunately. I mean, we parallelize them and we kind of do that stuff, but they take a very long time. Yeah.
If you roll out everything that's run to multiple servers, do you do this manually one at a time, or have you got a automated?
We have an automated thing. We call it a server-by-server deploy, and basically, we've done some kind of cat trickery that, we'll put one app server in like the list of servers, roll out the code, and then put the next one in, roll out the code, put the next one in. So, yeah, we pretty much, like I said, we automate pretty much everything. We don't really want to do anything manually. And it'll even pause in between, wait for the dispatchers to come back up to make sure that things are good before it goes on to the next server. So it won't detect errors. We generally, when we do deploys like that, we'll generally have like the Capistrano on one side and like a production tail on the other. And we have like scripts that will strip down like a tail down to like, the status code and a couple other relevant things. And we just watch it. And if all of a sudden like something starts going, we'll Control-C, and then we have cap tasks to unbalance. So we can look and say like, oh, we've done 2 of the app servers, now we're getting errors. One command will unbalance those 2, take the dispatchers down to those 2. So so it's not quite automated to that level, but yep.
When you do have to go down for a bit of time, do you try and set that up for the middle of the night? Do you know it's the middle of the day here in Australia?
Yeah, so as we go more and more international, maintenance windows become harder and harder to find. Generally, the middle of the night, even though it is the middle of the day here, is still generally the smallest, the smallest amount of traffic for all of our merchants. So our times move around. We generally look at we have lots of graphs. We look at our production traffic. We find the bottom of the peak that doesn't conflict with, nightly settlement processes. And then that's when we do our deploys. So for a long time, those were 3 a.m. Chicago time. They've moved around a little bit as we've gotten more and more international traffic, but generally we'll do server-by-server deploys, like the no downtime deploys. We'll do those during the day when everyone is fresh and most likely to be good. And then the stuff where we know we're going to pause traffic and could have a problem, we do those in the middle of the night. All right, I think that's it. If you have any other questions, come talk to me.